So we're going to start moving on to individual videos that will talk about different specific transporters. This slide is going to be talking about two kinds of ionophores. So ionophores are going to be substances that move ions. And specifically, both of the ionophores that we're going to learn about are passive mediated transporters. So again, making sure we sort of break apart and understand those words again. Passive means it's going to be operating in a downhill direction energetically. So downhill, meaning we are dissipating a proton gradient. I should say we are going to be talking about protons here, but this is going to be talking about dissipating a concentration gradient. Right? When we talk about something being passive, it happens without the input of additional energy. So passive mediated transport is going to dissipate a concentration gradient. We are going to be taking whatever substance is, let's call that substance A, and moving it from the high concentration side to the low concentration side. So again, that's the definition of passive. All of these systems that we're going to be talking about, since we're talking about specific molecules, proteins, so forth, that facilitate, are going to be mediated processes, meaning that we need a protein gate in order to sort of facilitate that. So this section is going to be talking about ionophores, which are passive mediated transporters. Okay, so I want to just sort of look at this picture first, and then I'll sort of translate how one particular system sort of operates here. So the idea with ionophores is they are basically going to be allowing us to move ions through membranes. So we can have what are called carrier ionophores, and those are going to be species that can pick up something on one side of the lipid bilayer and then allow it to be moved through to the other side. So we're going to learn about two different carrier ionophores. We're going to be learning about the drug 2,4-dinitrophenol, and we'll get to that on the next slide here. But we're also going to be learning about an antibiotic that's called valinomycin. So both of these are going to have properties that allow them to pick up an ion on the high concentration side. Their physical properties are going to allow them then to diffuse through the lipid bilayer, and then they can dump the ion out on the other side. So highlighting that when we're talking about 2,4-dinitrophenol, the ion is going to be protons. When we're talking about valinomycin, the ion is going to be potassium. Okay, highlighting that we will be learning about a channel forming ionophore. So again, this is going to be a transporter that allows us to move, in this case, potassium ions. So we're going to learn about the potassium transporter. Okay, and again, it is a passive mediated process. We're going to be dissipating a potassium ion gradient, moving potassium ions from high to low. Okay, so first story that we're going to talk about is going to be about sort of the drug 2,4-dinitrophenol. So 2,4-dinitrophenol. So I'm going to move sort of on to another slide here to sort of talk about the structure of this, do a little bit of review when we understand why and how this is able to sort of perform the chemistry that it does. But before we do that, we're talking about the movement of protons. And so inherent to this drug's ability to move protons is its ability to toggle between two different protonation states. Okay, so it's worth sort of doing a revisit of thinking about pKa values and how they relate to whether a molecule is acidic or not. So just as an example here, I'm going to talk about three molecules, 2 carbon molecules that have wildly different pKa values. Here is ethane. Okay, so we're going to be talking about the acidity of that hydrogen. Here is ethanol. Again, talking about the acidity of that hydrogen. Let's move these guys over just a little bit. And then talking about acetic acid. and the acidity of that hydrogen. Now, some of these pKa values you should already know. pKa's of alcohols are 15 to 16. pKa values of carboxylic acids are 3 to 5. We've actually done a lot with acetic acid, so that's maybe one that's up here, 4.78. When we think about the pKa's of alkanes, they are wickedly high, often higher than 30, like numbers that we don't even think about. But what I want you to do is understand why. Okay, so if you want to have an understanding of the acidity of a molecule, here's what I want you to do. I want you to deprotonate that molecule, look at the resultant conjugate base, and ask the question, how stable or unstable is that molecule? So let's do that with each of these. Let's deprotonate them and let's ask what we have. If we deprotonate ethane, any deprotonation is going to generate that conjugate base. It's going to be negatively charged. So what we're going to be doing is we are going to be putting a negative charge here on a carbon atom. Let's do the same thing here for ethanol. Deprotonation is going to put a negative charge on a single atom, but now it's on an oxygen atom. Let's deprotonate acetic acid now. Again, what might appear to be putting a negative charge on a single atom is not the full truth, right? Because we can draw resonance structures here where we move these electrons around and we have two atoms that can share in, sure, I have to move the electrons, can share in the ability to bear the burden of that negative charge. Okay, so in this first substance, we have a single atom that's bearing that negative charge, and it is a not electronegative atom. So we have no stabilization of the resultant conjugate base. Okay, move to ethanol. Now we still have a single atom, but it is much more electronegative. Oxygen is not unhappy bearing a negative charge. So we have a molecule that is more acidic. We have a pKa value that's lower. Remember, you can think about pKa as the pH you'd need to be at in order to remove that proton. So we go from having a pH of greater than 30 to having a pH that seems like it's in a normal range, pH 15 to 16, right? At least numbers that we think about biologically. Now, let's think about what happens when we go to our acetic acid. Okay, in this case, we are going to have two atoms that are able to share that negative charge, and that's again because of resonance. And those two atoms are very electronegative. So we are sharing that negative charge between two electronegative atoms, and so we see the lowest pKa value for carboxylic acids. Okay, so just a little bit of a review there on acid-base chemistry, being able to think about protonation state, pKa values, acidities. All of those are going to be really important skills to helping us understand systems, so it was worth sort of a review there. And so now let's look at the structure that we have for 2,4-dinitrophenol. So I want to do the same thing here. I want to draw the structure of phenol and compare it to, for example, ethanol that we have. So if we do this same sort of example and we think about how acidic is this proton with phenol, and you might not have known this, but the pKa for phenol, so again, this is phenol, pKa is around 10. Let's see if we can explain now why it is so much less than we see for a typical alcohol, okay? But maybe not what we see for the acidity of acetic acid. So what you want to do is you want to remove a proton, look at the resultant conjugate base and then ask, do I have the ability to help stabilize this? Okay, so I start out and I put my negative charge on an electronegative atom like oxygen. That's an alcohol. Phenol is an alcohol. So looks like it should be similar. So why doesn't it have a pKa same as most alcohols, is 15 to 16? And the reason is I have, with this aromatic ring, the ability to move my electrons around. So again, let's take these electrons, move them around here. I can move my electrons there. Let's draw this resonance structure. Okay. Now, I'm not going to draw the rest of the resonance structures, but hopefully you'll see here that if I move these electrons here, I can bounce my electrons to that carbon atom. So I'm going to be able to have that carbon atom, that carbon atom, that carbon atom share in the burden of that negative charge, as well as this oxygen atom. So 4 atoms, 3 being carbon, but multiple atoms is why we have a decrease in the pKa from that 15 to 16 that we normally see for alcohols down into a more reasonable range, okay? But we don't see the pKa that we do. This was only 2 atoms in acetic acid, but that's because those 2 atoms were 2 oxygen atoms that were both electronegative. Okay, so a little bit of a review there with what we see for our acidity. I want us to use that to understand what we see structurally with 2,4-dinitrophenol. So let's draw the structure of now 2,4-dinitrophenol. Okay, so here's phenol. Okay, so I'm going to draw phenol. And now I'm going to have at the 2 position and the 4 position nitro groups. So this again is 2,4-dinitrophenol. So let's kind of make sure we sort of see this. So the phenol is because of this part of the molecule, and then the dinitro is here. Okay, so we had a pKa of 10 for phenol, down from 15 to 16 for ethanol. So I'm going to tell you that the pKa of 2,4-dinitrophenol is around neutrality, right? Around pH 7, which means at physiological pH, it could sort of have either a protonated or deprotonated state. Okay, again, let's look at why that is. Let's deprotonate this guy. So if I deprotonate my OH, deprotonate it. If I deprotonate it, and I'm going to go ahead, I'm going to draw out the structures of my nitro groups here. Okay, and maybe you're already starting to see this here, but I now have an additional, I'm not going to draw out these guys just yet. I have more atoms that I can include in this resonance stabilization. Check this out here, right? If I take and I move these electrons down here, these electrons now, rather than going and residing on that carbon atom, can go to here, and then I can bounce my electrons out to there. So yes, I could put those on those carbon atoms, but importantly, I can move electrons now. And because I've got these nitro groups in these positions, I can take and bounce them out to 2 other oxygen atoms, greatly decreasing the pKa for this alcohol to a neutral sort of range. So, and we talked about this in class, but just to remind you, this is why a nitro group is an electron withdrawing group, because you can see it pulls electron density out from my ring. Okay, so it's an electron withdrawing group. Okay, so let's get to why this is a diet pill. Okay, what we really have is we've got 2,4-dinitrophenol that can toggle between these 2 protonation states. So again, I'm going to take and I'm going to just copy this here, and I'm going to show it in its protonated and then deprotonated form. So if I lose a proton, okay, I'm going to generate this molecule, and even though it can be resonance stabilized, I'm just going to show it simply as this guy. Okay, so I've got my protonated form and my unprotonated form. Okay, so here's why this is important. My protonated form is relatively nonpolar. It can diffuse through the lipid bilayer. My unprotonated form, right, cannot. So here's, and I need to grab one more piece of blank paper here because I want to talk about why is this important, okay? I'm going to come back here just for a second. My slides do not want to move on my tablet here. Let's do this. Okay. So why this is important is if these ions are protons, right? I have the ability of picking up protons on a high concentration side and then I'm going to become protonated and become uncharged so that I can flow through the lipid bilayer, get to the other side, and then I can dump them off. Remember, I've got 2,4-dinitrophenol that can sort of be in either protonation state. All right, so let's talk about why this is important. All right, remember when we talked about fuel oxidation, here's what normally happens with fuel oxidation, okay? Fuel oxidation, okay, so we can also refer to that as metabolism, is ultimately squeezing the electrons out of our molecules. We're going to then take those electrons to the electron transport chain, and we are going to generate a proton gradient. Move this over here just to give myself enough room. Proton gradient, and then that proton gradient is used to synthesize ATP. Okay, that's the purpose of fuel metabolism. Take a fuel, metabolize it, harvest the electrons, just putting in some pieces that we already know. We're harvesting the electrons in NADH, FADH2. Those guys go deliver the electrons to the electron transport chain. We build up a proton gradient. Let me just put in a couple of other pieces here. This happens in the mitochondria. Okay, we build up a proton gradient, and then we use the energy of that proton gradient to synthesize ATP. Okay, so essentially, we say that the entire process here is coupled. Okay, so this whole process is coupled. So going kind of from here to here is coupled. Okay, that whole process is coupled. We connect the energy in fuel to the energy in ATP. Okay. If we have some way of having an alternative path for that proton gradient, this is going to uncouple that process, okay? So that's essentially what happens here. Let me flip over and sort of grab these pieces here. So what I can have is I can have an unprotonated, I'm going to make this smaller here too so that I don't sort of take up so much space. Okay, I can have an unprotonated 2,4-dinitrophenol. This is going to pick up a proton on the high concentration side, right? Going from my unprotonated to my protonated form, I'm going to pick up that proton, and now I become uncharged. This molecule, again, can go through my lipid bilayer because it's uncharged, it's relatively nonpolar, go through the lipid bilayer, and then I'm going to drop off my proton on the low concentration side. So in essence, I've dissipated the proton gradient in this way, okay? The last little piece that I want to sort of highlight here is there is another an alternative path that we are going to study in this course, and it is called the use of uncoupling proteins. So uncoupling proteins, they are called UCPs. They essentially are going to do the same thing. They are going to dissipate this proton gradient. One other actually really important thing I forgot to mention with this. Remember the first law of thermodynamics? Energy cannot be created or destroyed. It's just converted into alternative forms. So what we have here is we have energy in fuel that's ultimately through this whole process translated to energy in ATP. Right? That energy is first made into a proton gradient, and then we use the energy of that proton gradient to synthesize ATP. Well, there's still energy in that gradient, and if it's not used to make a high energy molecule like ATP, if we dissipate it in another way, that energy cannot be destroyed. It's just converted into an alternative form. Here's what that alternative form is. It is heat. And this is an important piece that I haven't said about why we don't see 2,4-dinitrophenol as a diet pill, or highlighting even in the first place, why is it a diet pill? If we uncouple this process, if fuel is made into a proton gradient, but then we have this right turn that we make and we don't synthesize ATP, ultimately all of the energy in that fuel finds an alternative path. It's not worth the calorie content that it was. Right? That's why this was a diet pill. But here's why it was problematic. Thermodynamics, first law of thermodynamics says we can't create or destroy energy, just convert it into alternative forms. When we dissipate that proton gradient through this backdoor channel, that energy has to go somewhere, and that energy is made into heat. So herein was the problem of this diet pill. People didn't necessarily take them at the dosing that they were supposed to take them. 1 pill, good. 10 pills, great. So what would happen is internally they would generate such excessive heat that they had uncontrolled fevers that ultimately became fatal. They were doing so much uncoupling, so much dissipating of the proton gradient from their food that it heated up their bodies to a temperature that they could not control, and it became fatal. So you don't see 2,4-dinitrophenol anymore as a diet pill. But here's what you do see. You do see a natural mechanism for doing this same process, for uncoupling the proton gradient that's generated from fuel metabolism that's not used to synthesize ATP, but intentionally to generate heat. So uncoupling proteins are used to intentionally generate heat. And here's how and why that's important. You take something like a hibernating animal, an infant with a small body mass. What happens is these uncoupling proteins will use stored fuel, for example, in adipose tissue, to generate a proton gradient, dissipate that proton gradient, not through a molecule like 2,4-dinitrophenol, but through channels that are called uncoupling proteins that specifically move proton gradients and use that to generate heat. And you all of a sudden have a vehicle for keeping that hibernating animal warm when they're not physically moving. Did you know that when you are shivering, that's your body's attempt to try to use physical motion to generate heat? So this process is called non-shivering thermogenesis, generating heat not by shivering. It's important for hibernating animals to be able to do that because they're not moving to generate heat. It's also important for infants that have very small body mass, that are very sensitive to changes in temperature, to be able to stay warm. So where we see this, remember where the electron transport chain occurs. It occurs in mitochondria. So these uncoupling proteins are going to be found within mitochondrial lipid bilayers. Where do we find lots of mitochondria? Mitochondria actually will make muscle or adipose tissue very dark in color. That's why dark meat is dark in color, as it has a lot of mitochondria. Brown fat is very dark in color because it has a lot of mitochondria. Having a lot of mitochondria means it has a lot of these uncoupling proteins. You find a lot of brown fat in hibernating animals and in infants. Okay, so a lot to think about with all of that, but ultimately these uncoupling proteins play a very important biochemical process in thermoregulation in organisms that aren't able to do it by themselves. So just coming back, we had a lot of slides. They're coming back to this original slide here. 2,4-dinitrophenol, we can think of, again, as being this carrier ionophore that's going to pick up proton ions on the high concentration side. In being protonated, 2,4-dinitrophenol will be able to diffuse through the lipid bilayer, come across to the other side, and again, if it dumps its proton off, it actually can exit itself out of that lipid bilayer, okay, because it's now charged. But 2,4-dinitrophenol, again, an important molecule that dissipates proton gradients. And in our next video here, we will move on and talk about how valinomycin does a similar kind of process, but now for potassium ions.